All right, well, welcome back everybody to asymptotics and perturbation methods. We're coming towards the end of our treatment of asymptotic expansion of integrals. There's just today's lecture and maybe one more. And after that, we'll start talking about asymptotics for algebraic equations and then the real heart of the course on differential equations. But okay, so we today are going to illustrate the idea that often it's very helpful to think about problems in the complex plane. You know, up till this point in the course, we haven't really relied much on complex analysis. There was a little hint of it in the last lecture when we had a contour integral to evaluate. But today, I think you really will be a little bit at a disadvantage if you haven't taken a course in complex variables. But this is really the only time in the whole semester that would happen. So hang in there, don't worry about it too much. And if nothing else, it might motivate you to take such a course because you'll see where those ideas can get used. All right, so let me begin. We're going to talk about a method called Steepest Descent, which is a really clever, beautiful method that generalizes the two methods we've been talking about recently, Laplace's method and stationary phase. They can almost be seen as like the real and imaginary parts of the method of steepest descent. You'll see what I mean in a second. All right, so let me share my screen with you. All right. Okay. So there's a lot of writing here, and so I don't know if this is helpful to you guys or not, but I wrote out a bunch of stuff ahead of time. And tell me if I'm going too fast. You know, I mean, that's the danger with writing out things ahead of time. But I wanted to leave time for really showing you the nitty-gritty of the calculation, which there I will be working in real time with you. Okay, so here we are, method of steepest descent. If you do want to read about it in Bender and Orsog, that would be section 6.6 of their book. And so let me set this up by trying to explain what I'm talking about, where I say that it's related to Laplace's method and stationary phase. So first, just a quick reminder from Laplace's method, that was 2 lectures ago. Remember that was concerned with real integrals, with integrals that had a function phi up here in the exponent that is real. And that was the method where we were talking about sharply peaked, you know, bell-shaped functions phi, and the region right under the maximum makes the biggest contribution to the integral in the limit as the integral gets increasingly sharply peaked as x goes to infinity. All right, so that method is terrific for problems of this type, things that look like this. And it can give us the whole asymptotic expansion, not just the first term, but the full expansion, where the only errors, if we care to go that far, would be the transcendentally small terms. But it does require thinking about this function phi as being real. Now, I'm emphasizing that because if you contrast the method with stationary phase that we did in the last lecture, you'll notice that has an exponent that is pure imaginary. Right? There's an I times x times some function that we call psi of t. And there, rather than thinking about bell-shaped behavior, we were looking at rapid oscillations in some oscillatory function as x goes to infinity. And then it was in the neighborhood of a point of stationary phase that we got the dominant contribution to the integral. Now that method only gave us the leading term, which we saw was often of order 1 over square root of x. Generically, that's what you would get. And then there are errors that are kind of uncontrolled by this method that are order 1 over x, which we could not calculate with the method of stationary phase. Often we don't care. Usually the leading term is good enough. We saw how fantastic it was for approximating Bessel's function J0. Nevertheless, there could be circumstances where you want more than just the leading term. And so the method we'll do today will show us how. Okay, so we've got these 2 types of methods with phi real or with a pure imaginary exponent. Steepest descent improves and generalizes on both of those methods as follows. So now we're going to consider integrals of the type in the box here, in the red box. For some reason, the book has switched to calling this modulation factor h of t rather than what we used to call it f of t, but whatever. So there's some function here. And then we have e to the x, and then something in the exponent rho, where now we're going to think of rho as being complex. It can have both a real part, that's like our phi in Laplace's method, or it can have an imaginary part, like our psi in stationary phase. And actually this rho, we're going to think of as having both a real and an imaginary part put together in such a way that the result is an analytic function, meaning that this rho is an analytic function of the complex variable t. It has a nice derivative in the complex t plane. And so once we do that, we're now opening the door to all the methods of complex variables and complex integration. And so we're going to think of this I of x as really being a contour integral in the complex t plane, rather than, up till now, we've been thinking of t as just living on the real axis. At the moment, that's where the integral is taking place, on the real axis. But we are going to be able to deform that contour off the real axis and hopefully be able to evaluate the integral more easily by doing that. So here, this variable t, as I say, is now thought of as a complex variable, u plus iv. And so the big idea is we started out by wanting to do a problem here on the real axis from A to B, but we'll find it advantageous to deform the contour to something that comes off the real axis, still joins the same endpoints, but with the property that this function psi that was in the imaginary part of rho, the condition will be that we're going to choose a contour such that this psi will be constant on that piece of the contour. That's the very clever idea. Deform the path of integration to one along which psi is constant. Now that may not be possible to achieve completely, so we may have to settle for psi being constant on each piece of a contour. That is, the contour will be made up of several pieces, and psi will be constant on some of them, but not necessarily the same constant. We can also allow pieces of the contour that will not contribute anything to the integral, often in some limit as some parameter goes to infinity. But anyway, I don't want to get into too much detail now because we'll be seeing all the details when I do a concrete example in a few minutes. But for now, that's the big idea. Let us deform the contour to something where psi is constant. Now, why would we do that? I mean, what's the advantage of doing that if it's even possible? Well, watch what happens if we can achieve that. The integral we're interested in, which was h of t e to the x rho, now can be written as e to the x phi times e to the x psi. And so if we're able to achieve psi equals constant, then this term will be constant and can come outside the integral. And so we would then be left with this e to the ix psi that's constant, and then we have something that looks like it's all geared up for Laplace's method. So what this will do for us, I mean, if you want to think of it this way, by saying psi equals constant, you've made the phase psi completely stationary. I mean, it's constant. So I kind of like to think of this as like a method of superstationary phase. It's not just that psi prime is 0 at one point. Psi is identically constant on pieces of the contour. So that really eliminates the cancellation effect and can give us a big contribution to our integral. All right, so anyway, that's the overall strategy. Look for those places where psi is constant, pull the term out of the integral, do Laplace's method, and then all the advantages of Laplace's method come with that. You can get the full asymptotic expansion as x goes to infinity. Okay, so that's the basic strategy. Now, that was kind of, vague. I'll show you concretely. But before I do a concrete example, you may be wondering, why is this method called the method of steepest descent rather than the method of constant imaginary part, right? I mean, that would seem like a better description, since that's what I'm really doing, demanding that psi be constant, have a constant imaginary part. but they're the same thing. That's the cool idea. Or that's one of the cool ideas. Insisting on steepest descent turns out to be the same thing as choosing a constant imaginary part. So in the sense that this function phi changes most rapidly, in particular will descend most rapidly, most steeply on a curve of constant psi. So let me clarify what I'm talking about there. This is a simple idea that comes from multivariable calculus. You would have thought about these things back when you were learning about the geometric interpretation of the gradient. Those of you who are teaching assistants, which I know a lot of you are, when you teach multivariable calculus, you always tell the students that the gradient vector points in the direction of fastest increase of the function that you're taking the gradient of. So let's see how that relates to what we're doing here. So let's just to be very specific, let's suppose I had the rho function being t squared, where remember t is a complex variable. If I had that case, then plugging in the complex variable t equals u plus iv and then squaring it, and remembering that I squared is -1, you'll get u squared minus v squared as the real part, and then plus 2iuv. So the imaginary part is 2uv. And so in our notation with psi and phi, this real part phi is just this stuff, u squared minus v squared, and the imaginary part psi will give us 2uv. Okay, now think about this for a second. So what are the level sets of these functions? Actually, let's focus really on the function phi. I mean, because that's the one we're interested in. We're interested in when phi changes or descends most rapidly. So think about where phi doesn't descend at all. Think about contours of phi where phi is constant, the level sets of phi. And so maybe you recognize these things. If I said like u squared minus v squared equals constant in the UV plane, that's a high school analytic geometry question, right? U squared minus v squared equals constant defines a branch of a hyperbola. And so does UV equals constant, by the way. I mean, right? UV equals constant. That looks like a parabola that asymptotically approaches both axes in the UV plane. So if I graph these, let me graph the level sets of phi, like say phi equals 1 or phi equals 4. That would be the parabola or hyperbola. U squared minus v squared equals 4, which would be something that goes through 2. That's why I chose the number 4, so that I can put a dot here on u equals 2 on the u axis. And then, it's something that looks like this, and then asymptotically approaches the line u equals v, if I went way out there. But anyway, so I have some little piece of the hyperbola that looks like that. And similarly, if I did a level set having a value of 1 or having a value of 9, you get those hyperbolas. And now imagine, think of these like a contour map of some weird terrain, and you're standing here at altitude 9. If you wanted to go downhill as fast as possible, steepest descent, then the move is to go at right angles to the contour. This would be the path of steepest descent, always going at right angles to the blue contour lines. Right? Familiar, I hope, this kind of idea. But what's so nice is that this exact path that is following the path of steepest descent is itself given by an arc of a hyperbola, the hyperbola uv equals constant, where the constant is defined by going through this point. So that's a well-known fact that these families of hyperbolas actually, everywhere they intersect at right angles. Beautiful family of orthogonal curves. And so what we're seeing here is that the curves of constant psi, namely these kind of hyperbolas, are the paths of steepest descent relative to the blue hyperbolas. So that's what I'm trying to say, that the curves of constant psi in this example give me the paths of steepest descent down the function phi. And that's a general fact about analytic functions. It's not any peculiarity about this function t squared, rho of t equals t squared. I've just shown it here because I know you know this geometry about hyperbolas, but it's a really wonderful fact that you prove in a complex variables course that this works in general. If you have any analytic function rho, and you look at its real and imaginary parts, they will obey this orthogonality property that I just mentioned, so that the curve of steepest descent down the phi function, the real part, will be level sets of the imaginary part, the psi function. So this is proven in the book on page 287, 288, and the proof uses more technology from complex variables called the Cauchy-Riemann equations that just come from the analyticity assumption, and also the facts from multivariable calculus that the gradient of phi points in the direction of fastest increase, or also if you go backwards on it, fastest decrease of the function phi, and the further fact that the gradient of phi is always perpendicular to the gradient of psi from the analyticity assumption. That the Cauchy-Riemann equations will give you that. So anyway, this is a bunch of stuff that you either have seen before, or if not, you can just trust me. But the upshot is that the method of steepest descent really is tantamount to the method of constant imaginary part. Okay, so that was all preliminary stuff. And now I want to start diving into an example, and I'll slow down. But maybe this is a good point to pause and see if you want to ask anything so far. Either in the chat or out loud is fine. Or if I'm good, I will just proceed. Okay, you feel pretty good about the setup anyway? I mean, it's a nice strategy, very clever. This is a 20th century technique. This was not known to Lord Kelvin. I did check the history, by the way, of stationary phase. So it was 19th century, as I had thought, and it's often attributed to Stokes as well as Lord Kelvin. So it was people working in fluid dynamics who thought about these issues early on, and also wave problems in optics for a stationary phase. Okay, anyway, so let's now move along. Here's my little warm-up example. I mean, but this will illustrate the main ideas for the method of steepest descent. And it's taken from the book on page 283. All right, so there it is. It's an integral of e to the I x t squared, but it doesn't go over minus infinity to infinity or anything like that. It kind of what makes it difficult is that it just goes from 0 to 1. If it went all the way out to infinity, we could do it exactly. But here we're only going to do it asymptotically as x goes to infinity. It's not a very convenient definite integral. But okay, so this is the kind of thing we recognize. I mean, it's got a pure imaginary exponent. So we could hit it with the method of stationary phase. And if we do, well, all right, so then we get our standard kind of answer with the 1 over square root of x dependence. And we'll get this prefactor from the method. So this is the kind of thing we did last time. But we also pointed out that the method doesn't give you the correction terms. And so there's some mysterious amount of potentially 1 over x stuff coming from the rest of the integral away from the neighborhood of the point of stationary phase. Sort of integration by parts would suggest that we would have terms of this size left over. But anyway, what can we estimate that? So with steepest descent, the answer is yes, we could get this next term. All right, so let's see how. So if we're going to apply steepest descent to this problem, now I'm ready to start writing. I haven't written anything out ahead of time. Let's see what we would do. Okay, got to get limbered up. Good. All right. So we're in the t-plane, and so we write t equals u plus iv. And so actually it's very similar to the calculation I just did a moment ago. T squared is, as before, u squared minus v squared plus I to uv. But the problem is I've got this little extra I here in front, so it's going to interchange what used to be the real and imaginary parts when I put in everything. So that is, if I write out what I of x is now, I'll have I of x equals integral from 0 to 1, e to the ix, and a bunch of stuff in the exponent, u squared minus v squared plus I 2uv. That's all dt. And so cleaning that up a little bit, now multiplying through to get the what's the real and what's the imaginary part, we have a real part. So the i's multiply together to make a -1, and I have an e to the minus 2 x u times v. And then there's another term, e to the ix times u squared minus v squared. dt. All right, so now remember the philosophy. We're going to try to pick some kind of contour in the complex plane that joins 0 to 1, such that, let's see what we have so far. All right, I've got in the t plane, think of it as the UV plane. Currently, I'm going from 0 to 1. And my path of integration is just on the real line. Okay, but I want to replace that with some new contour. Joining those two endpoints such that, well, we want the imaginary part up here to be constant. This would mean that u squared minus v squared should be constant, if possible, or at least piecewise constant on some piecewise defined contour. So pick a new contour such that u squared minus v squared is constant on each piece of the contour. Now, notice, by the way, that this function psi in this example would be u squared minus v squared. And we're getting, psi equal, if we look at the endpoints, we have psi equals 0 at the point 0, 0 over here. Whereas we're getting psi equals 1 at the other endpoint at 1, 0. So there's actually no way to join those 2 points with a contour that has a constant psi because, right, the value is 0 at one end and 1 at the other. So we're going to need something that has pieces, but that's okay. The endpoints are on different pieces. Of the new contour. They will have to be. All right, but we can live with that. Now, so let's just focus on one endpoint at a time. How about 0? That looks easier. So at the endpoint, at 0, 0, we just decided psi is equal to 0. So if we want to ensure that psi is constant, psi equals constant on the piece through the origin, then what we're saying is we're interested in where psi itself is equal to 0. And from the expression above, that, well, I mean, psi is just u squared minus v squared. So that tells us that we need u equals plus or minus v. To be a piece of the contour. Now, if you think about what that looks like, that's going to be obviously two straight lines. So there's one of them, and there's the other. So there's our 0. Here's 1 way over here. We're not thinking about 1 yet. Now, one of those pieces is going to be the one we want, and one of them is not. So these are the kinds of issues that come up in this method. You have to, part of the art is to construct the good contour, the new contour. And so let's discuss the kind of reasoning that we're going to use. Actually, maybe before I discuss how to choose the pieces, let's look at the other endpoint just to see what level of complications we're going to have to contend with. So at the other endpoint, there we said psi was equal to 1. Right, I mean, that endpoint was u equals 1, v equals 0. So psi equals 1, let's see what that is. So that's now of the form, I mean, u squared minus v squared, which is psi, is equal to 1. That's giving us something that looks like this. Right, we already discussed those kind of hyperbolas. And on this hyperbola, depending how you want to write it, you could think of it as, like up here, v is equal to the square root of u squared minus 1. Or if you would prefer, we don't know yet which is a better way to write it, we might think of it as u equals square root of 1 plus v squared. On there. So this is where, you know, like psi equals 0 on here, psi equals 1 on here. Down in this part, v is equal to the negative. Let's not do that in red. V is the negative square root of, sorry, u squared minus 1. On that part. Remember, this is the UV plane I'm looking at. Okay. So now let's think about this. We're trying to deform the contour that is currently going like this to some new contour that somehow connects these 2 points. We don't know what we want. So let me tell you the answer. I'll show you the answer to save time, and then we'll see why it's the answer, like why it has certain desirable properties. If you wonder how in practice you would do that, well, maybe you would try something wrong, and then you would see what was going wrong, and then you would erase it, and then you would eventually arrive at what I'm going to show you up front. So I claim that what you want to do looks like this. Let me redraw it. This turns out to be the good contour. You take this branch up. You go, now you somehow have to get over to this hyperbola. That is going to come down to, you know, this endpoint. And the way we're going to do it is by connecting these two with a bridge that goes like this. And I'll say it's going at a constant height. I'll call it capital V. So there's U. This is the V axis. And this is what I meant when I said earlier that you might have a piece of the contour which does not have constant phase. Psi is not constant on this, right? It's going from psi equals 0 to psi equals 1 across there. So the phase is changing like crazy on that top bridge, but it's going to turn out that the bridge will not matter because I'm going to consider the limit of capital V going to infinity. And as I take that capital V out to infinity, the contribution from here is going to go to 0. That needs to be shown. We have a bunch of things to check. But it's these kinds of considerations that dictated why I chose this particular contour rather than something like, say, back here, you might have thought, well, why can't I go like this and then over to here and then that way? That you could draw that contour and it'll just make the problem much harder. You won't get the wrong answer, but you'll have to deal with canceling out some infinities. Whereas if you do it here, you'll get a bunch of finite stuff, some zero stuff, and then some more finite stuff. So it's just, oh, and I'm using implicitly here something that you should know from complex variables. The whole concept of deforming the contour is that the integral from here to here is the same as the integral from here along this path. This is Koshi's theorem, and the fact that the thing we're integrating is an analytic function of t. So you have path independence. Okay, so now I have a bunch of stuff to calculate. And actually, I want to explain why this was the good choice. So let's try to do that next. All right, so the key in understanding why did we choose this contour is, first, look at how does the function phi behave on these pieces. So let's look at the choice here. On this piece, we know u equals v. That's how we chose that line. So there, on the line u equals v, remember phi was defined as negative 2uv. We had that earlier. That was the real, in the e to the x phi, that was what the phi came out to be. So on u equals v, this boils down to minus 2v squared, since u equals v. And what's nice about that is this has the desirable property or the advantage that phi decreases from phi equals 0 to phi equals negative infinity. As v runs from 0 to infinity. So what am I talking about there? I'm saying, if I look back at my picture, and remember, I'm thinking of lifting the bridge out to infinity. You have to examine what's happening along this path. And what's nice about it is that the function phi has its maximum here, and then it just decreases monotonically out to negative infinity going this way, which means when I integrate e to the x phi, I'm getting the biggest contribution from this point, because that's where phi is maximum. Remember, in Laplace's method, you're interested in the max of phi, right? You want this sharply peaked bell around the max. The fact that the max is occurring here is good. If the max were occurring out at infinity, that would be confusing. So this is what's good about this. That's why we choose this contour piece rather than this. If we had chosen this one, we would have phi would increase to its maximum out here. And that's no good. That's too confusing. So, I mean, just to write that down, whereas, I mean, we're not going to do it this way, but whereas on u equals negative v, phi increases. I mean, so maybe I should first finish this thinking. This is good, what we did earlier, because the max occurs at t equals 0. At 0, 0. Whereas if we were on u equals negative v, that's nasty because phi is then increasing from 0 to infinity. And the max would occur out at t equals infinity, which is not good. We want phi to have its maximum at some finite point. Okay, so all of that is really an aside. We're not going to calculate that wrong thing, but that's the kind of thing that would go wrong if you had chosen that first. All right, so where are we? We're looking at this problem. We've decided that this has got some desirable features. And now let me similarly show that this hyperbola, this choice, rather than something down here, that this piece also has desirable features. So similarly then, on the hyperbola, which let's call it u equals, this is a good parameterization, u equals square root 1 plus v squared. What's happening there? Well, the function phi that we're examining, which was negative 2uv, becomes negative 2v square root 1 plus v squared, where I've just replaced the u. And here again, we're thinking of v as running between 0 and infinity. As you can see from the picture, right, that v, we're in the upper part of the v uv plane. V is out here, v is going out to infinity. We're coming in from infinity down to v equals 0. So anyway, on that piece of the hyperbola, what's happening with phi? Well, this also has a good property. Again, the same good property. Good, phi is a maximum. namely phi equals 0, at the point u equals 1, v equals 0, at that nice finite point, the right-hand endpoint of our contour. And it decreases to phi equals negative infinity as v goes to infinity. So what I'm saying is, on this piece of the contour over here, this piece, the dominant contribution is again coming from this endpoint. This is where phi is maximum on this whole contour. It's negligible out here where it's going out to a phi value of negative infinity. I mean, although that phi is negative infinity, remember it's up there in the exponent. It's an e to the x phi. So having a negative infinity, we're only getting transcendentally small contributions from stuff out there. Okay, so with this contour, we're getting whopping contributions from these 2 points and their neighborhoods. And hopefully then the last thing we'll have to show is that we're getting nothing of interest from the bridge. Okay, but let me pause there with this kind of reasoning that I've been doing. Let me name the pieces of this contour, and then I'll take your questions if you have any. I'm going to think of this contour as having 3 parts that I will call C1, C2 is the bridge, and C3. So you want to ask anything about the strategy or the big ideas, what needs to go, what we're considering?
So far, we've just needed the contour to be in the upper half plane and getting taller and taller. We haven't used anything about the fact that psi is constant on those pieces yet.
That's right. Correct. We haven't used that at all yet. Yep. Yeah, that's right. That's coming right now. Well, actually, maybe I should dispense with the bridge. I mean, because that's a nice little analysis style estimate. And then after I show that the bridge is irrelevant, we'll calculate what happens on each of those 2 curves, C1 and C3. But yeah, you're right, Mark. We haven't used psi equals constant yet. So actually, why don't we just see what's happening on the bridge? So there, so on the bridge C2, we don't have psi equals constant. But it doesn't matter. Since the integral of e to the ixt squared dt along C2 goes to 0 as this quantity, capital V, that's defining the bridge, goes to infinity. Now let's see why that's true. So let's estimate the size of this integral. Integral over C2, we had written it out as e to the minus 2 x uv e to the ix u squared minus v squared dt. All right, so let's, as usual, estimate this by taking its magnitude as a complex number and doing a triangle inequality style estimate that in complex analysis amounts to saying the magnitude of this integral is less than or equal to the integral of the magnitude of the integrand, dt. And so if I look at the magnitude of these 2 terms, there's this term. Well, that's going to be it. That's fine. That's just going to get copied. The interesting one is this, because e to the anything real has magnitude 1, right? E to the I theta is a point on the unit circle for real theta. And so that is something of magnitude 1. And so we can say that this is less than or equal to, yeah, right. So the magnitude of the integral less than or equal to the integral of the magnitude, which gives me less than or equal to integral over C2 e to the minus 2x uv. And then, like I say, this has magnitude or modulus, whatever you want to call it, equal to 1. And then dt here. And I didn't need any absolute values because e to the minus 2x uv is a positive quantity. This, by the way, in regard to Mark's comment, I mean, this is another reason why we're working in the upper half plane rather than the lower half plane, because you can see from this that when x is a big, x is going to positive infinity, we're getting something that looks like negative big number. We want this v to be positive so that it stays a negative big number up there in the exponent so that this will be negligible. Otherwise, it'd be a big positive number, and that would cause trouble. Okay, so now what? Well, actually, here's why it was clever to choose v equals constant on the bridge. Now we can just do this integral. So on C2, this is just equal to the integral from, think of it as, like the left endpoint u1 to u2. So here, what am I thinking? When I say dt, this is du plus iv, but that's just du because v is constant on this contour. It's been fixed at the level capital V, so it has no differential, or its differential is 0. So anyway, I'm integrating from u1 to u2, e to the minus 2x capital V times u du. And that's an easy integral from freshman calculus, e to the minus 2x capital V times u1 minus e to the minus 2x capital V u2 all over 2xv. Skipped a step there, but I think you can check that that's right. And that's really small. I mean, it's being divided by capital V. It's got a big X in the denominator. It's got exponentially small terms in the numerator. I mean, there's a lot of reasons that that is small. So this is definitely going to 0 as big V goes to infinity. Okay, so the bridge is negligible. So we're going to ignore C2. All right, so let's take stock of where we are here. As V goes to capital infinity, sorry, as capital V goes to infinity, I meant to say, I of x is equal to C1, integral over the contour C1, e to the minus 2x uv e to the ix u squared minus v squared dt plus, so I'm just getting contributions from my two surviving curves, C1 and C3. Same thing. And I'm going to call these I1 plus I3. Okay, so I'm going to evaluate those separately. Okay. So let's first do I1. All right. So on there, we're on the curve C1. And we decided that that was following the straight line U equals V. And so dt, I mean, I'm just going to rewrite the integral now that I know what curve I'm integrating over. dt is just d of, I mean, I set U equals V, so it's V plus IV. So this is just 1 plus I times dV. And so my integral over C1 that I'm trying to calculate is 0, I'm not going to say 0 to infinity, because I've taken capital V up to infinity. So I'm integrating from 0 to infinity. Let's just look at all this stuff here. So maybe I should look above. What am I doing? I'm setting, whoops, I'm setting U equals V in this expression up here, and I'm setting U equals V right there. Right? So this will boil down to, and then I've also replaced the dt now with this little calculation for dt. So this is giving me integral from 0 to infinity e to the minus 2x. Since u equals v, this just becomes 2x times v squared. This term, e to the ix, u equals v, so this is 0. This is e to the 0, which is 1. So I don't even have to write it. And then times dv, which is my 1 plus I, or sorry, times the dt, which is 1 plus I dv. And, well, I can factor out the 1 plus I. And then you'll notice I have a Gaussian integral sitting there. Which, you know, Laplace's method wants to eat for breakfast. Actually, we don't need Laplace's method because we just have an exact Gaussian integral that we can read off the answer with gamma functions or whatever we've memorized. The polar coordinate trick, do it however you want. Anyway, so this comes out to be 1 plus I, and then this integral gives me 1/2 square root of pi over 2x. Just skipping that step. And if you want, you can write that in complex notation with an e as 1/2 e to the I pi over 4 square root of pi over x, which might look familiar to you because that is the leading term that stationary phase gave us. This is the result from stationary phase. I wrote it down earlier, but you might have forgotten. So we've recovered that part, and it's not surprising in a way because, I mean, if you'll forgive me, let me just blow back in my pages here. So where would that be? Yeah, it was on this page. I said stationary phase gives, right, this that I just wrote down, plus this unknown term. So we just recovered this, and in a way, it shouldn't be surprising because if you did apply stationary phase, where is the point of stationary phase? Well, here's the phase, t squared, and when that has a derivative 0, that's t equals 0, meaning the origin. So the point of stationary phase was the origin, and we've just been working around the origin. So we got that contribution. But the thing stationary phase misses is the contribution from this point. And that's what we're now going to get. All right, so let's continue. Now that's coming from C3. All right, so let's do the third integral then, I3. Okay, so here, let's just take a very direct approach. If I have time, I might show you a more clever approach, but the very direct and like literal approach using the method, there's a shortcut that I'm not showing you, but I'll just do it kind of naively. So the direct approach, to estimating I3. Oh, could I say one thing actually before I proceed with that? You notice we didn't make any approximations yet. This is exact up here. I haven't done any asymptotics yet. All I did was deform the contour and show that as capital V goes to infinity, that bridge disappears. So this is all exact. And even I1 has been calculated exactly. So there's no approximations yet. But we're going to start getting some approx. That's why I say estimating about I3. Now we're going to start getting into some approximations. So let's see. The direct approach is, let's just use V as the integration variable. Excuse me. All right, so on C3, on C3, what did we have? U squared minus V squared is 1. And so U, we said it could be written as 1 plus V squared. Okay, so our integral on C3, let's copy everything down, is, what am I supposed to do? E to the minus 2x, and then I can go uv, but I have this nice expression for u, so I'll say v times the u that I just wrote down, 1 plus v squared. I want to make sure my v's are distinguishable from my u's. There's that term. And then there's also, what else? Let's just stare at what we have. What am I doing? I'm supposed to be looking at this kind of expression. So I've just substituted for u. But now what about this business? U squared minus v squared. Remember, we're on a curve of constant phase. I mean, we've chosen u squared minus v squared equals 1, right? That's the hyperbola. So this term is just 1, which means this e to the ix, as advertised, can be pulled out of the integral. And so what's happening right here is I have e to the ix as my next term. Yeah, this is where the stationary phase, keep saying that. This is where the constant imaginary part is really helping us. Constant by design. Right, so that comes outside the integral. And I have e to the ix, integral over C3, e to the minus 2x. Actually, now that I've changed variable, let me further change variables. Well, no, I want to write it as a v integral, right? That's what I said. Use v as the integration variable, was this comment up here. So rather than thinking of t as my variable, let me convert to v. How would I do this? I've got this relationship here that's holding along the curve. So let's just work off on the side for a second. Actually, maybe I'll just copy what I have so far, and then we'll work off to the side. 2xv square root 1 plus v squared. I have the e to the ix outside dt. And now I need to work on this dt for a second. So what's going on? T is u plus iv. So dt is, well, du plus idv. But now use the fact that u equals square root of 1 plus v squared on the curve. So du, take the differential of that, and we get, so let's see. I'd have a square root 1 plus v squared down here in the denominator. There's a factor of 2, and then there's a chain rule term, 2v, and then dv. These 2's would cancel out. Right. So this becomes, when I simplify dt, I'm getting v over square root of 1 plus v squared plus I all times dv. There, I think I've done that correctly. And so, taking stock, what's going on here, just look above. We're doing the integral over C3. And so the integral over C3 is exactly, no approximations have been made yet, ladies and gentlemen, e to the ix integral from, we started up at the bridge, way up at the top, and then we're coming down. So we start at v equals infinity, come down to v equals 0, e to the minus 2x v square root of 1 plus v squared. And then a funny looking replacement for dt, which is this v over square root 1 plus v squared plus I dv. Okay, let that soak in for a second. This is still exact. Now, it's nasty, but it's exact. So we haven't done any asymptotics yet. Now we can finally do them. It's this integral, which we can hit with Laplace's method by observing that, you know, this term, remember, has its max at v equals 0 down at the endpoint. And as x goes to infinity, this expression is becoming sharply peaked around the max. And so this is the only time we're doing anything asymptotically, and it's all now set up for Laplace's method. And so if we're sufficiently careful here in our power series manipulations, we could generate the full asymptotic expansion. But let me just pick off the leading term, because that'll still be enough to give us our correction to stationary phase. So the maximum of the, you know, the e to the x phi, well, so that's e to the minus 2x v square root of 1 plus v squared on v going from 0 to infinity. The max of that occurs at v equals 0, as I keep saying. So if I just want to do leading order to get this correction term, you can be really crude about it and say that the integral over C3 will be asymptotic to e to the ix. So let's see what I'm doing. I'm copying the expression in the top line up here. The most brutal approximation you could make for small v is this one. You could say this is e to the ix. Remember, what am I trying to do? I would want to expand around v equals 0. Anything that needs expanding, like these square roots, those can get expanded around v equals 0. So the most brutal expansion you could do is to just substitute v equals 0 into these terms. And that's sufficient to get the leading order. You could do better, but this would be good enough for now. So I'm not going to change these limits. This is still infinity to 0. E to the minus 2xv. And then I'll just sort of write this term as 1 plus ... That was my brutal expansion of the square root. And then I can also do the bracket equally brutally. It's just going to be I plus, if I substituted v equals 0, there will be lower order terms. And then dv. And that's all a pretty easy integral to do, right? Because then I'm just integrating minus e to the minus 2xv dv times I. So then you can calculate that leading order term to be e to the ix, and then you get a minus I over 2x. It comes out. Which is pretty nice, because what that's saying is then that our integral, which we know is I1 plus I3, is asymptotic. Take everything into account. Here was the stationary phase term, e to the I pi over 4 square root pi over x. And then plus this term that we just calculated, minus I over 2x e to the ix. Which you'll notice is of order 1 over x. That was the big O 1 over x term that we could not get with stationary phase, but now we have it. And like I say, if we wanted more terms, we could just be more careful about the ... dots. So it's order 1 over x as expected. All right, do you want to ask anything about this? It looks like I do have time to show you a shortcut, so maybe I will. But the floor is open if anyone wants to raise a comment at this point. All right, maybe you're eager to see the shortcut after all that Herculean labor. Well, all right. Yeah, I think maybe I can do this in the remaining time. I may end up going a little bit over, in which case you could watch this on video afterward. But okay, so here's a little bit slicker approach to finding I3. Which is, remember that when we're doing calculations with Laplace's method, which is what we ended up having to do here at the end, it's only the infinitesimal neighborhood of the max that matters. So there's no point using the exact hyperbola that goes through there. Only care about the infinitesimal neighborhood near the endpoint. So we could just use the tangent line to the hyperbola at that point. And that will be good enough, because that's infinitesimally all that the integrand sees. So we will just approximate the curve C3 by its tangent line. At the endpoint, where t equals 1. Right. And that's, as I say, because the max of phi we know occurs at t equals 1. And the detailed shape of C3 is irrelevant. The detailed global shape of C3 doesn't really contribute anything. Only the neighborhood of, and when I say neighborhood, I really mean only the infinitesimal neighborhood. Of t equals 1 matters. As we saw earlier when thinking about Laplace's method, the rest contributes transcendentally small terms that don't show up in the asymptotics anyway. I mean, the rest outside the neighborhood. Okay, so this is sort of the 2D analog of 2D in the complex plane analog of the reasoning we used in Laplace's method. When we went by going from like minus epsilon to epsilon and replaced it with minus infinity to infinity, arguing that doing that only introduced transcendentally small terms anyway. Okay, so with that way of thinking, what we would do is make a new contour that looks like this. I would take my old straight line like that, still take my bridge, and then all I'm interested in is this neighborhood of this one point at 1, and the tangent line is just a little vertical piece of the hyperbola. And then I can do anything I want to get to that. Because that's not going to contribute anything anyway. So this is the key part right there. That little vertical piece that's tangent to the hyperbola. And so the new contour is, or let's say the important part, the important piece of the new contour is, think of this point, this is at t equals 1 plus iv, where v is a small thing. Say v going from 0 to epsilon. So I just use that. And this stuff out here gives me transcendentally small terms. So take the part that matters, and then you get I3 is the integral over C3 e to the ix t squared dt. That was our original notation for the problem we're doing. And now we can just substitute this very convenient 1 plus iv. So let's see what we get here. I have integral from 0 to epsilon e to the ix 1 plus iv all squared idv. And actually, I should do one little thing, which is that this should have a negative sign in front of it, because remember, I'm going downhill. I'm going down, right? This is coming this way. So we start at epsilon and go down to 0. So it really wants that negative sign there. And, well, let's evaluate this a little bit. So what am I getting? According to my notes, I'm getting minus I e to the ix integral. Now, in the spirit I mentioned of Laplace's method, where I can take from 0 to epsilon and suddenly replace it with 0 to infinity, because I'm only, again, throwing in pocket change of transcendentally small terms, do that. And you get in here e to the minus 2x v. And then I've expanded this square up in this exponent. And then there's an additional term. E to the minus I xv squared dv. And I replace this with its small v expansion, 1 minus ix v squared plus ... so that I can read off the answer in terms of gamma functions. Right, I'm using the fact that up here v was small. So I'm just expanding this for small v. And then later making this move of going out to infinity at the cost of these transcendentally small terms. So anyway, if you do all that, and I'll let you check the Gaussian integrals, you end up getting that this is asymptotic to minus I e to the ix over 2x. And doing just the two terms I had written down here, you get 1 minus I over 2x, which this first term was what was found on a few minutes ago. And this is yet another term. I mean, just to really show off, we've now got 3 terms in the asymptotic expansion. And you see it was very easy doing it this way once you understand what you're doing. So, okay, that is really the virtue of this slick approach. It's much easier to generate the higher order terms if for any reason you want them. All right, I thank you for your patience. I'm sorry I went a couple minutes over. The floor is open for any questions that you may have.
So is this the method of steepest descent that we have seen in all the numerical analysis courses? Is it the
You
same
have
thing?
seen in, sorry, you saw in what courses?
Like numerical analysis for just iteration and approximating nodes and stuff like that, using the method of steepest descent. I am just wondering if they're connected in any way.
Well, that's interesting. I'm guessing what you mean when you speak of the method of steepest descent in the context of numerical analysis is that you have some complicated function, and then you choose, you're looking for a minimum of the function maybe, and then you follow a gradient vector to go.
Yeah, exactly.
Yeah, so that would, I guess that's called method of steepest descent also. I think of it as conceptually related. They're not the same method. One is just follow a gradient downhill on a function to get to a lower point. We're doing some of that, but I mean, here we're really very much using the machinery of complex analysis, which I don't think comes into the calculations in numerical methods for, I think I would usually call what you're describing the method of gradient descent. But I guess some people call it steepest descent. Anyway, it's slightly different from what we're talking about here, but same in spirit. Yeah, okay, good. I see a comment in the chat. Or someone who want to ask a question out loud? Right, so Yubo says, I've just heard it called gradient descent. Yeah, that's what I would call it too. But anyway, yeah, it's taking you the steepest path downhill. Did someone else have a comment or question?
Would the higher order terms be the same between using the slick method and if we had treated the if we'd kept things out besides just the leading order in the first approach that we took?
Sure. This would give you the same answers.
Okay.
If I kept these dots and showed what they really were. Sure, you can do it. So, you know, nowadays, probably people don't even bother with worrying about this because after all, Mathematica has a function in it built in called asymptotic that one of you I think actually it was you, Jackson, who pointed it out to me. So I'd be curious, should we just ask Mathematica to do asymptotic on this integral? I would be interested to see how good it is. Let's try it. Anyway, this method should work. Have you already tried it? You did? With
No,
math?
no, I have to play around with it sometime.
Let me try it right now. I have no idea what will happen, and I'm not too skilled at it yet. I'm going to stop sharing this screen and share my desktop. The other day I was giving a talk and somebody commented that they like my wallpaper. I guess they like this picture. This just comes built in with the Mac. It's is this Big Sur, maybe? Those of you from California. I don't know, or Catalina, I don't know. It's a Mac wallpaper. All right, but where am I? I want to look in Mathematica. I need to make this big for my old man eyes, 200%. And then I have to teach myself how to use the asymptotic functionality. And does it have something called asymptotic integrate? Oh, it does. Hello. So asymptotic integrate, and how does that work? Tell me, Mathematica, what do you do? So it shows how to asymptotically integrate sine tx. Okay, so let me try this, and I'll just mimic this. I love the way this is written with these examples. So I'm going to say asymptotically integrate exp of, our example was ixt squared, I believe. Does it know I, or do I need a special symbol for that?
You need capital I.
Capital I, thank you. Ix t squared. And I'm supposed to say t goes from 0 to 1, and then I'm going to say x goes to infinity. That might work. Let's see what it does. All right, so it gave us stationary phase. You can't see it? Right, that's what we got from stationary phase. So it gave one term. Now, there's a method, I think it lets me choose whatever order I want, doesn't it? If I look for more information, computes an asymptotic approximation to an order n. Wait. Oh, here it says compute a leading order asymptotic approximation. Where do I,
So I think instead of the notation x goes to infinity,
yeah,
the notation that you'll use is brackets x, comma, infinity, comma, and then the number of terms that you want.
good man. Thank you. X comma infinity. Let's ask it for 3 terms, which I think we just did with our supposedly slick method. Ooh. Well, that's interesting. So 3 terms, that's a little more. It even did one more than I did. I think the one I just did was only 2 terms. Okay, we're not as good as a machine. I like, though, that it's taking a second to run. So this term, with the -1 to the 1/4 power, that's the e to the I pi over 4 term. That this is stationary phase right here, the 1 over square root of x term. Here's a 1 over x, which is the thing that I just calculated by the direct approach. And then here's the term, I hope. Yeah, right. No, wait. If I'm looking at my notes. Yeah, this term right here with the 4, the -1/4 x squared e to the ix, that was what I got from the slick method. So it's fine. I guess you might be wondering then, why take this course given that all of this can be done in no time in the computer? And I suppose the answer has to be that there are a lot of interesting ideas in here. Even if, for actual computations, you probably want to use the machine. Yeah, so I think it's really more for the ideas than the results. That this, hopefully this stuff is valuable. The other argument could be that some of the people who are at the cutting edge of numerical methods, like what you're seeing in this symbolic manipulation program, like our own friend and colleague, Alex Townsend, he uses asymptotics to make extremely fast numerical methods. So you can use numerics to supplement what computers can do or to enhance what computers can do. That is, you shouldn't assume, that computers just do it on their own. If you build in some clever asymptotics, you can make them wicked fast, which especially becomes important for high dimensional problems, say 3-dimensional fluid flow or even higher dimensional stuff in some other fields. So I think there's still a place for asymptotics. I hope so. Anyway, too late now, you're in the course. All right. So I better stop. See you next time.